Introduction. If you are out in the open during a thunderstorm, a safe place to be in is inside a car. In this lesson, you will learn the meaning of electric flux, Gauss's law, derive Coulomb's law from Gauss's law, use Gauss's law to derive the expression for the electric field strength due to a charged sphere, a charged plate. A way of visualizing the electric field patterns is using electric field lines penetrating a surface perpendicular to the lines. The number of lines per unit area represents the electric field strength. The electric flux phi is the number of electric field lines passing through a surface area. Click on the correct answer. Move the slider to 30 degrees. The number of electric field lines through the area A is the same as the number that go through A prime. The flux phi through A prime is equal to the flux through A and is given by phi equals EA cosine theta. Click the definition button. Summary. Electric flux phi through an area A is phi equals EA cosine theta, where E is the electric field strength and theta is the angle between the normal to the area A and the direction of the electric field. Gauss's law gives the relation between the electric flux through a closed surface, often called a Gaussian surface, and the charge enclosed by the surface. Gauss's law is given by phi equals sigma q over epsilon naught, where phi is the flux through a closed surface sigma q, the algebraic sum of the charges enclosed by the closed surface, and epsilon naught is the permittivity of the medium. Now we will use Gauss's law to derive Coulomb's law. Click on point charge positive q and observe the electric field around the charge. Click the Gaussian surface button. Click and drag each of the Gaussian surface into the electric field. Which is the most suitable Gaussian surface which reflects the symmetry of electric field pattern? Answer: the sphere with its center at the position of the point charge positive q. Click on the derivation button. Summary. Electric flux phi through an area A perpendicular to the electric field E is phi equals EA. Gauss's law, electric flux phi equals sigma q over epsilon naught, where sigma q is the algebraic sum of the charge enclosed by the closed surface, and epsilon naught is the permittivity of free space. Gauss's law can be used to derive Coulomb's law. Click on the sphere to show how a metal sphere is charged by induction. Click the sphere again to ground the sphere. Click on the sphere to observe how the positive charges redistribute on the surface of the sphere. Why does the positive charges behave this way? Answer: the positive charges distributed uniformly on the surfaces of the sphere due to the forces of repulsion. Drag each of the Gaussian surface to the electric field due to a charged sphere and choose the one that is the most suitable. Click the derivation button to observe how Gauss's law is used to derive the expression for the electric field strength E outside the charged sphere of radius r and charge on the sphere is Q. Click the Gaussian surface button. Now click the derivation button. Click on the sphere to observe the graph showing the variation of the electric field strength with distance r from the center of a charged sphere. Now, can you explain why passengers inside the car are safe from the high voltage discharge? This is an example of Faraday's cage. Answer: the passengers are inside a charged conductor, so the electric field strength in the car is zero. Click at the center of the hollow metal sphere to place a point charge positive Q at the center of the sphere. Click the sphere to observe the charges induced on the inner and outer surfaces of the sphere. Click the sphere again to earth it. What is the electric field strength at surfaces X and Y? Drag the correct charge and electric field strength in the relevant boxes. Summary: the charge on a charged sphere is evenly distributed on its surface. The electric field strength E at a distance r from sphere of radius r with charge Q is E equals Q over 4 pi epsilon naught r squared for r greater than or equals to big R. E equals 0 for r smaller than big R. A large conducting plane surface is uniformly charged with a surface charge per unit area of sigma, charge density. Click at various points of the conductor to observe the electric field. Use Gauss's law to derive an expression for the electric field strength due to the charged plane. We need to select a suitable Gaussian surface. Click the Gaussian surface button and drag each surface that reflects the symmetry of the electric field. The most suitable Gaussian surface is the cylinder. Click the derivation button To derive the expression for the electric field strength at the point P in the electric field due to the charged plane of charge density sigma. The electric field strength close to an infinite charge plane is independent of the distance from the plane. Summary. The electric field close to an infinite charge plane is perpendicular to the plane. The electric field strength E close to an infinite charge plane is E equals sigma over epsilon naught.